So we are developing a better model of the atom. When we left off in an earlier chapter, we had the Rutherford model of the atom with the positive charge in the nucleus and the electrons moving around. But what we want to do is take the data from line spectra that we saw in the previous video and use it to develop a model that will tell us how the electrons move around the nucleus. Now this becomes quite theoretical for a little bit. I'm going to rely on your patience. This will come back to explaining experimental data again soon, but we may have to suspend some disbelief for a little while in the middle. Hope I tell you a good story. Let me try. Now what we saw in the previous video was that when I excite an atom by giving it energy, it releases that energy back as light, colored light. We only see particular colors, and that implies that the atom can have only particular energies. So I'm going to propose an energy level diagram like I see on the left-hand side of this slide. What I have here is the energy of the atom, and we're going to say that the energy of the atom is quantized. It can only have certain allowable levels. I'm going to label this first energy level as n equals 1, where n is the number of the energy level. That's the lowest energy state. The atom could also have the energy represented by the line I labeled n equals 2, n equals 3, and so on, up to n equals infinity. What I've shown here with the atom in the ground state, that's the state before I give it electrical energy. Everything wants to be in its lowest energy state, like me on the couch after dinner. But if I give it some energy, some electrical energy, as this arrow is implying, the law of conservation of energy says that energy must go somewhere. The electrical energy goes into the atom absorbs the energy, and the atom then hops up to a higher energy state. Now, a couple of things before I forget and move on. I'm talking first about the hydrogen atom only. Nice to start this simple story with the simplest possible atom. The other thing you might see is that the gaps in energy are not all the same size. I'll explain that for you later. So the summary for this slide is that the energy of the atom is quantized. There's only certain allowable values. The atom can have energy in the n equals 1 state, or it could have the energy associated with the second energy level, or the third energy level, or the fourth, but it can never be in between. That's kind of funky, huh? How would it get from the first energy level to the second energy level if it could never have an energy in between? The analogy that we make is that it's like going up the stairs. I can go up 1 step or 2 steps, but I can't go up a half a step. Now, this is just showing a very simple case where a single hydrogen atom absorbs exactly the right energy to go from the first energy level to the second energy level. But in the real hydrogen lamp, there will be many different atoms getting excited at the same time. So these arrows are showing a variety of possible absorptions. One of the atoms could jump from the first energy level, which we call the ground state, up to the second energy level, as indicated by the arrow whose tip is right here. Or it could make a jump of 2 steps to the third energy level, or another atom could make a jump to the third energy level, but it can't jump in between. We could also have some atoms that were already at the second energy level. They'd already been promoted that far. They can get promoted higher. So there's a lot of different absorptions you can get when you have a large collection of hydrogen atoms. Now, we're not going to see anything when that happens. We're going to only see what the light when they hop back down to the lower energy levels. So we're going to look not at absorption anymore. The energy was already absorbed to make excited atoms. Now we're going to look at emission from excited states, higher energy states. So again, first energy level, second energy level, third, all the way up to n equals infinity. And what we can see is that the atoms can drop to lower energy from any one level to any other level. What do we see when that happens? Law of conservation of energy says that energy has to go somewhere. When the atom loses energy by changing energy levels, that's the symbol delta, which always means the change in energy. That energy goes from the atom into a photon of light. And the law of conservation of energy says that the energy that the atom loses is the same as the energy the photon gains. Just one little thing I should clarify here. There is a negative sign here. When I put a negative with an energy, that just tells me which direction the energy is going. When energy goes into something, we say that the energy is positive. When energy comes out of something, we say it's negative. And that's why there's a negative sign in that equation. The energy that goes out of the atom is the energy that goes into the photon. We saw in an earlier slide that the equation for the energy of a photon is E equals h nu. So I can also express the energy that comes out of the atom as equal to negative h nu. All right, here's the good part. Because I can only see certain allowed energy changes, say from the second energy level to the first energy level, or from the third energy level to the first energy level, but not in between. Because I see only certain energy changes, I can see only certain frequencies, only certain energies of photons, only certain colors. So my model that has allowed quantized energy levels for the hydrogen atom explains why I get only certain colors. But I haven't yet told you what is happening in the atom that makes these allowed energy levels. And here comes the evolution of the atomic model. This model was proposed by Niels Bohr in 1913. There's my friend Niels Bohr. And he has a model of an atom here. There's the proton in the nucleus. He said that the allowed energy levels in the hydrogen atom corresponded to certain orbits that the electron could have. He said it was like a solar system, and the electron could orbit around the nucleus. He said that the first energy level, which we called n equals 1 in our energy level diagram, corresponded to the lowest energy orbit. And that's where the electron would live until we put the electrical energy into it. When we excite the atom, we can give it some energy, we can pull it to an orbit further from the nucleus. And it makes sense that I would have to put energy in to do that. Protons are positive. There'll be an attraction to the negatively charged electron. So if I'm going to pull the electron further away, I'm going to have to put some energy into it. So the electron's in a higher energy level when it's in a higher energy orbit. Bohr said that the second energy level corresponded to an orbit at a higher distance from the nucleus, and so on and so on. Now this picture only shows the first 3 energy levels, but there would be an infinite number of orbits to represent the infinite number of energy levels that we can have. So what Bohr said was, when I put electrical energy into the atom, I move the electron from the first orbit out to a higher energy orbit. Then it's going to want to jump down again to emit the energy to get back to a lower state. So here in this picture, I have an electron that's in the third energy level, and it can hop back to any lower energy level. In this picture, it's hopping down to the second energy level. It could hop to the second energy level. It could have hopped to the first energy level, but it couldn't have hopped anywhere in between. Bohr didn't know why it couldn't be in between, and that puzzled him. But the data spoke to Bohr. The data said that if you could only get certain energy levels, You can have only certain transitions in your orbit. Now, what we're going to do to add to your belief in this model, I'm actually going to do a calculation that shows what color light we could get if the electron hopped from the third energy level to the second energy level. But before we do, I'm going to have to change this slide I took off the internet, the picture I took off the internet. I'm going to have to put a negative sign in there. Remember, on the previous slide, I said that the energy change for the atom is the negative of the energy of the photon. The energy that comes out of the atom when the energy is emitted will go into the photon. All right, now let's see how I'm going to do that calculation. A mathematician working at the same time as Bohr proposed this equation for the energy of an energy level in a hydrogen atom. And you remember I said I would give you all the equations that you needed in the red boxes. Your job was to know what they meant. So this is the equation for the energy of an energy level in a hydrogen atom. Here's the form that it has. In the numerator, I have a bunch of physical constants, and you recognize some of them. That H is Planck's constant. Already talked about that. That C is the speed of light. Already talked about that. The capital R is called the Rydberg constant, and maybe I'll write it over here. Rydberg. And its value is 1.097 times 10 to the 7 reciprocal meters. Remember, I'll always give you the physical constants. The variable on the right-hand side of this equation is the energy level N. And you remember that I was labeling the energy levels in my energy level diagrams with N. N equals 1, N equals 2, etc. That's the N in the formula. Now, Bohr said those energy levels corresponded to different orbits. First orbit, second orbit, third orbit. Before I get calculating things with this equation, let me give you a qualitative sense for this. I get absorption of electrical energy when it goes to a higher energy level. When the electron hops to a higher energy level, I get light emitted when the electron hops to a lower energy level. Let me just make a little note of that. A photon of light is emitted when an electron in the hydrogen atom jumps to a lower energy level. Which Bohr said corresponded to a lower energy orbit. Now, not to frustrate you too much, the Bohr model still isn't the most modern model. We don't believe in orbits anymore, but I don't think our time will be wasted considering this. It's a nice evolution of a model. So I promised you I was going to calculate the color of the light when the atom hops from the third energy level to the second energy level. Here we go. Calculate the wavelength of the photon emitted for the n equals 3 to the n equals 2 transition. And here is the symbolism that we use. That means the electron's hopping from the third orbit down to the second orbit. All right, now we had a relationship. We said that the energy change for the atom was related to the energy of the photon. And it's the photon I want to know about. So let's see if I can work with the known thing. Let's see if I can calculate the energy change for the atom. Delta anything, the change in anything, is final minus initial. So that's the final energy level of the electron minus the initial energy level of the electron. On the previous slide, I gave you a formula for the energy level. That was negative RHC over n squared. And I'm going to put n final here to make it the final energy. I'm going to subtract negative RHC over n initial squared. Well, I can simplify that a little bit. I've got a common factor. Let's pull out a negative RHC, and I'm left with 1 over n final squared minus 1 over n initial squared. That's going to make it less complicated when I actually put the numbers in there. R, the Rydberg constant, is 1.097 times 10 to the 10 to the 7. No, yeah, 10 to the positive 7. I had to look that up because we don't memorize things, right? Planck's constant H, 6.626 times 10 to the negative 34 joules times seconds, times the speed of light c, 2.998 times 10 to the 8th meters per second, times 1 over n final. Well, this was the 3 to 2 transition. It ends up in energy level 2. Minus 1 over n initial squared. It started in energy level 3. So let's tap that into my calculator. Let me see. I've got that here. There's no point in me wasting your time saying those numbers. Just look at the units here. 1 over meters, meters in the denominator, cancels meters in the numerator. Seconds in the denominator cancels seconds in the numerator, and I'm left with joules. Woohoo! That's a good unit of energy. Energy is in joules. So that gives me some confidence. The other thing you'll notice is that this calculation gives me a negative number, negative 3.027 times 10 to the negative 19 joules. That negative, when attached to an energy, just says whether the energy is going in or out. And what that says, because it's negative, is that the atom lost energy. Okay, we finished a hunk of this problem. We, back at the very beginning, said that I could find out about the photon if I knew the energy lost by the atom. So, now that I know the energy lost by the atom was negative 3.027 times 10 to the negative 19 joules, I know that the energy gained by the photon is positive 3.027 times 10 to the negative 19 joules. Good thing that's positive. It doesn't make sense for a particle of light, a photon, to have negative energy. Now, where are we going from here? The question wanted the wavelength. So let's see if we can remember some relationships involving the energy of a photon. These will always be provided to you. I will remind you here that the energy of a photon is h nu. Wait a minute, that has frequency, not wavelength, and it's wavelength that I want. So I'll also remind you that c equals lambda nu. So what I can see is I could know the wavelength if I knew the frequency, because c is a constant. I can know the frequency if I know the energy of the photon, because h is a constant. Hey, wait, I do know the energy of the photon. So here I go. I want the frequency rearranged to be nu equals E over Planck's constant, 3.027 times 10 to the negative 19 joules, divided by Planck's constant, 6.626 times 10 to the negative 34 joules seconds. And I'll tap that into my calculator. I got 4.568 times 10 to the negative 14 joules. Let's double check those units. Joules in the numerator cancels joules in the denominator. Oops, units are wrong. I didn't do that on purpose. That leaves me with seconds in the denominator. 1 over seconds. Seconds to the minus 1. Hertz. Good. That's a good unit for frequency. All right, why did I find the frequency? So that I could find the wavelength. And rearranging this equation, I see that the wavelength is the speed of light divided by the frequency. When you're problem solving for your reader, your job is to teach them. So it's good to explicitly show the symbols you're working with, the equation you're working with, unsubstituted. Then explicitly show the numbers that you're using. And here comes the frequency, which I saved in my calculator memory so that I don't get round off error. All right, put that in my calculator. I get 6.563 times 10 to the negative 7, and I better be more careful with my units now. 1 over seconds in the numerator cancels 1 over seconds in the denominator, leaves me with meters. Hey, that's reassuring. I want a wavelength. Meters are a good unit of wavelength. This is a perfectly good answer to the question. The question was calculate the wavelength associated with it. But I'm trying to sell you a story here, so I'm going to make one more conversion. I'm going to convert that into nanometers. And you would not memorize this. You would have to be given that a nanometer is 10 to the negative 9 meters. So we get 656.3, oops, that's funny looking, 3 nanometers. A lot of calculation there. Let me summarize. What this is saying is that when an electron in a hydrogen atom jumps from the third energy level to the second energy level, I will see light with a wavelength of 656 nanometers. Let's go back to the emission spectrum of hydrogen. (656 nanometers). Hey, look, there's angstrom up there. That's an angstrom is 10 nanometers, is a tenth of a nanometer. In nanometers, this is 600. That's 700. 656 is about here. Hey, when we emit, when the electron hops from the third energy level to the second, we see red light at exactly the same frequency that it truly is observed. So this lends support to the Bohr model. It explained data we already see. Okay, we've explained the red light. What about the blue-green light and the blue and the violet? Here's the exciting part. Can you handle it? So here's a picture of the Bohr model of the hydrogen atom. First energy level, first energy level here, second here, and so on and so on. And we calculated that when we went from the third energy level to the second energy level, that was 656 nanometers, and that was red. We could do more calculations. When we go from the fourth energy level to the second energy level, that will turn out to be the blue-green line in your spectrum. From the fifth to the second, that's the blue. From the sixth to the second, that's the violet. So this model perfectly matches the observed colors in the hydrogen line spectrum. Pretty funky, huh? These lines, it's called the Balmer series of lines. Those are the colors that we observe. Now, I remember learning this, and what I wondered was, what was so special about the second energy level? We see those colors when the electron hops to the second energy level. Why wouldn't it hop back to the first energy level? Well, it turns out it does. Not only does this model explain the known data, it helps people go look for more data. When it hops from the down to the first energy level, let's go over to this energy level diagram on the right. The Balmer series only drops to the second energy level. But if I take hops down to the first energy level, that could be any one of these transitions and so on, you can see that the energy jump that it makes, the change in energy, delta E, is much bigger. More energy change for the atom, more energy goes into the photon. More energy of the photon, higher frequency for the photon. Higher frequency, lower wavelength. And when they calculated that, they saw that they got the wavelengths in what's called the Lyman series. That part of the spectrum is not observable to the human eye. That's in the ultraviolet part of the spectrum. And guess what? When they went and looked for those lines with an ultraviolet spectrometer, they were observed exactly where they were predicted to be. Similarly, there's a bunch of lines observed in the infrared part of the spectrum for transitions down to the third energy level. So no wonder that Bohr's model was accepted. It explained previous results and it predicted new results. Still leaves a couple of questions though. First of all, why do you see all the colors at once when you turn on the hydrogen lamp? Even when there's a low pressure of hydrogen gas in the lamp, there's many atoms doing the absorbing of the electrical energy and emitting the colored light to get back down to lower energy states. Now here's the sad part of the story for you. Well, not so sad. I told you that this is still not the final model of the atom. The Rutherford atom was proposed in 1909. Balmer proposed his model in 1913. And less than a decade later, we replaced Bohr's model with a new quantum mechanical model, which is the one we believe in. But don't worry, just like every other evolution of the model, we keep some features and just refine it to have it explain new data. So when I come back in the next video, I promise you, I will tell you the most current model of the atom. One last pitch. This is a rich story that I can't tell you in the half hour it took me to tell you this, to do this video. I hope that all along you've been reading your text, making sense of it, making lists of questions from it. Make lists of these questions, please, and bring them to our Zoom meetings.